So welcome you back to today's module. So in the last module, we were discussing a relationship between the invariant test, the sufficiency, and the uniformly most powerful unbiased test. So one result which we did in that direction was that any UMPI alpha test is unbiased. So UMPI alpha test is always unbiased. The second result which we did in that direction is that if UMPI alpha test exists, and if there is a UMPU alpha test which is also invariant, then the UMPU alpha test would be UMPI alpha test. So if you know the existence of a UMPI alpha test, and there is a UMPU alpha test which is also invariant, then such a UMPU alpha test would be UMPI alpha. So that makes life in many situations simpler, but still in those situations you'll have to prove that UMPI alpha test exists. Then only an invariant UMPU alpha test would be UMPI alpha. Then we realize that let us apply the sufficiency first, because sufficiency and invariance both do some kind of a data reduction. So what I do is, first I do a data reduction through sufficiency. Now whatever sufficient statistic I get, they might have a certain probability distribution. I write down my null hypothesis and alternative hypothesis in terms of these parameters which are already there. So now the question is, I now apply invariance to this sufficient statistic under a certain group of transformations. Now the question is whether now the UMPI alpha test which I get is the same as if the invariance was applied to the original data x1, x2, xn. And then we said that we did not prove it, but we said that, look, if your group of transformations is such that it is indexed by a parameter c, which is a subset of Rn, n-dimensional Euclidean space. So like GCX as x1 plus c, x2 plus c, xn plus c, GCX as cx1, cx2, cxn, or GABX as ax1 plus b, ax2 plus b, axn plus b. So in each of these cases, it is characterized by a c, which is either R, or c, which is 0 to infinity, or AB, which is a subset of 0 infinity cross R. So in each of these cases, I can first apply the invariance, and then I can apply, first I can apply the sufficiency and then invariance. The test would be same as if you applied invariance to the whole data to begin with. To see some examples in that direction, we were doing the following example. So let x1, x2, xn be IID, normal mu sigma square. My theta is mu sigma square, or mu sigma, you can write it down, belonging to R cross 0 to infinity. Sigma naught is a fixed positive constant. Now consider H naught, that mu is greater than or equal to sigma naught square, sigma square is greater than or equal to sigma naught square versus H1, that sigma square is less than sigma naught square. Let us consider this. So first I need to identify the group of transformations under which the problem is invariant. So if I consider, you see, if normal mu and sigma square both are unknown, I know that this whole family is invariant under a affine group of transformations. So G could be collection of all those GAB such that A is positive, B is in R, where GAB x1, x2, xn is nothing but ax1 plus b, axn plus b. The question is, under this group of transformations, can I say that my P0 and P1 both are invariant? Now note that under this transformation, ax1 plus b, ax2 plus b, axn plus b are again IID. What is the mean? Mean of a mu1 plus b? H0 doesn't talk about mu, so it says some mu, so a mu1 plus b. A mu plus b would be some point in R, so that is okay. What would be the variance? Variance would be a square sigma square. Now note that if I change sigma square to a square sigma square, the hypothesis changes, H0 changes. So, because it becomes a square sigma square is greater than equal to sigma naught square, which is equal to sigma square is greater than equal to sigma naught square by a. So it is not invariant. So that means I need to take a to be 1. So not invariant. So P0 and P1 are not invariant. Now I've got the hint what I should take. So I should take my G to be GCs, C belonging to R, where GC of x1, x2, xn is same as x1 plus C plus C. Now this is invariant. Why? Because x1 plus C, xn plus C are IID, normal, mu plus C, and variance remains the same. So I see what happens to H0 under the transformation. H0 says that sigma square is greater than or equal to sigma naught square. Now if I apply the transformation, it says variance, which remains the same, is greater than or equal to sigma naught square for some mu. So mu has become mu plus C. That doesn't matter. My set of distributions is same because set of distribution is nothing but normal mu sigma square, where mu is in R and sigma square is greater than or equal to sigma naught square. So here also mu is in R and sigma square is greater than or equal to sigma naught square. Similarly under H1, because sigma square doesn't change, sigma square is less than sigma naught square means here also sigma square less than sigma naught square, and there is some mu, some mean. So P0 and P1 are invariant under G. So that means P0 and P1 are invariant under the additive group, which is nothing but additive group. All right. So now I need to see a maximal invariant statistic. So suddenly maximal invariant statistic would be nothing but function of d1, d2, dn minus 1. So T x is invariant if and only if T of x1 plus C, xn plus C is same as T of x1, x2, xn for every C belonging to R. Now since C is belonging to R, I have a 1 degrees of freedom available to you in terms of parameter C. I can take C to be minus x. So this implies that T of x1, x2, xn is nothing but T of x1 minus xn, xn minus 1 minus xn, and 0. So which is some function of d1, d2, dn minus 1. Where di is nothing but n minus 1. So this implies that any invariant statistic will be a function of d1, d2, dn minus 1. And also the statistic d, which is d1, d2, dn minus 1, I see whether it is invariant or not. It is invariant means if I apply xi plus to each of them, whether di changes or not. If I apply xi plus c to each of them, x1 plus c and xn plus c, because of minus sign, c gets cancelled. Same thing happens everywhere. So this is invariant. This implies that d is equal to d1, d2, dn minus 1 is maximal invariant. So what I need to do is I need to find out what is the PDF of d1, d2, dn minus 1. So to get the PDF of d1, d2, dn minus 1, first I get the PDF of d1, d2, dn minus 1 and xn. So the PDF of d1, d2, dn minus 1 xn at point, let me call this as d1, d2, dn minus 1 and t. So the PDF of d1, d2, dn minus 1 xn at the point d1, d2, dn minus 1 t is, so I have to make a transformation that di as xi minus xn for I is equal to 1 to n minus 1 and t is same as xn. So that means xi becomes di plus t for I is equal to 1 to n minus 1, xn as t. So of course Jacobian would be, you can see, would be upper triangular matrix with diagonal elements as 1, 1, 1, 1, 1, 1 and 1. So Jacobian would be 1. So I look at the PDF, of course we know that it is not going to depend on mu. So what should be this? This would be nothing but what I do is I put the, first I look at the joint PDF of x1, x2, xn, which is nothing but 1 by twice pi sigma square to power n e to power minus 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square, right? And yeah, and then I put in terms of d and then mod of Jacobi, right? At I can put x is equal to d plus t, d vector plus t, where d vector is, I can define dn to be 0, right? So this says, if I look at, this is same as I have defined only d1, d2, dn minus 1. So if I dn to be 0, my xi for I is equal to 1 to n become di plus t. So xi is nothing but di plus t for I is equal to 1 to n, where dn is 0. So x becomes d plus t, right? Xi is di plus t, so it becomes forever. And Jacobian turns out to be 1. I can write down this as 1 upon summation I is equal to 1 to n xi minus x bar whole square plus n times x bar minus mu whole square. So this becomes 1 by twice pi sigma square. So this will be n by 2, e to power minus 1 by 2 sigma square. Actually this whole thing, if you see, this is nothing but summation I is equal to 1 to n. Let me write down before. This whole thing is nothing but summation I is equal to 1 to n xi minus x bar whole square plus n times x bar minus mu whole square, right? And it subtract x bar. So cross product term because of summation xi minus x bar would become 0. So you get summation xi minus x bar whole square plus n times x bar minus mu whole square. So I put all those values. Jacobian is 1, so it becomes 1 by 2 pi sigma square to power n by 2 e to power minus 1 by 2 sigma square summation xi minus x bar whole square. Now xi is same as di plus t. Xi is same as di plus t. So x bar would be nothing but d bar plus t. So xi minus x bar would be nothing but di minus d bar whole square. So summation I is equal to 1 to n di minus d bar whole square. Note that I have taken my dn to be 0 and d bar is nothing but d1 plus d2 plus dn upon n. Okay, plus n times x bar is nothing but d bar plus t. So d bar plus t minus mu whole square. Jacobian is 1, so that is okay. So let me write down d1, d2, dn minus 1 and t. There is a t also, right? I have to get a joint PDF of d1, d2, dn minus 1. So joint PDF of d, which is d1, d2, dn minus 1, is I just integrate out t over here. So h sigma dt, and I just integrate out unwanted variable t. So let me put this as h sigma star. So h sigma dt dt. So joint PDF of d1, d2, dn minus 1 I am denoting by h sigma star. So what I have to do? I have to here integrate out t. So what it happens? Now note that if I see t, this goes outside, there is no t over here. So e to power minus 1 by 2 sigma square summation I is equal to 1 to n di minus d bar whole square goes outside. This becomes 2 pi sigma square to power n by 2. And then n by 2 sigma square t minus mu minus d bar whole square. So that is like a normal density with mean as mu minus d bar and variance as n upon variance as sigma square by n. So this becomes sigma by root n, sigma root 2 pi, variance into root 2 pi. So this is what this turns out to be. So now this is one kind of a hypothesis, sigma square less than or equal to sigma naught, sigma square greater than or equal to sigma naught square, again sigma square less than sigma naught square. Density is this. I know from a result which we did, if this has MLR, then the uniformly most powerful test among all densities of this type would exist. So I need to see whether for sigma 2 greater than sigma 1. So because what has happened? Finally I have reduced that under H naught my density is this, with sigma square greater than or equal to sigma naught square. H1 density is same with sigma square less than or equal to sigma naught square. So there is only one parameter over here. By a result for uniformly most powerful test for one parameter, I know for testing H naught sigma square greater than or equal to sigma naught square, H1 sigma square less than sigma naught square, UMP alpha test exists, provided this has MLR. So I just need to check for sigma 2 greater than sigma 1, H star H star sigma 2d upon H star sigma 1d. So these constants would get cancelled. So what you are left with? E to power 1 by 2 sigma 1 square minus 1 by 2 sigma 2 square summation I is equal to 1 to n di minus d bar whole square. So what does that mean? So that means this has MLR. This is increasing in summation I is equal to 1 to n di minus d bar whole square. So what is UMPI alpha test? Phi naught. This is equal to 1 because under H1 you have to H1 that sigma square less than or equal to sigma naught square. It is increasing in di minus d bar whole square, so that means it would be, you will reject if summation I is equal to 1 to n di minus d bar whole square is less than or equal to chi square n minus 1 alpha, and of course you can divide it by sigma naught square 0. And what is this? Probability of rejecting H naught under H naught is alpha. So that means so this would be 1 minus alpha, sorry. On the right of it, this is 1 minus alpha. This chi square on n minus 1. And this is chi square n minus 1, 1 minus alpha. Why? Because I'll see that summation di minus d bar whole square is nothing but summation xi minus x bar whole square, because if I can show that, then this distribution chi square n minus 1 alpha is obvious. So let us try to see why I have said so. In fact, what I should have done is, first I should have calculated summation xi minus x bar whole square. So let me say that from here I go to what is summation I is equal to 1 to n di minus d bar whole square. That you can see is nothing but What is di? Di is nothing but xi minus xn. In either case, for I is equal to 1 to n. So what would be d bar? D bar would be the mean of this thing, which is x bar minus xn, right? Because each xn is there in each of them, whole square, which is nothing but summation I is equal to 1 to n xi minus x bar whole square, which you know has sigma naught square chi square on n minus 1 under sigma is equal to sigma naught. So the correct step should have been, this comes later on, I opt for this. So now from the result for uniformly most powerful alpha test, you know that the UMPI alpha test is phi naught x is equal to 1 if statistic Tx, which is summation I is equal to 1 to n xi minus x bar whole square is greater than c, 0 otherwise. And how do you use this c? So this c is chosen so that probability that under sigma naught square summation I is equal to 1 to n xi minus x bar whole square. Sorry, it would be because under h naught it is sigma square is less than c. So you'll reject h naught if less than c. Is less than c is nothing but alpha, right? You get the maximum liberty which is given to you. So this same as pre sigma naught square summation xi minus x bar whole square by sigma naught square is less than c by sigma naught square is equal to alpha. Now when sigma is same as sigma naught, I know that this has a chi square on n minus 1. So that means c by sigma naught square is a point, so that on the left of that point the area is alpha. So I look at this point chi square on n minus 1 PDF. Suppose this point is chi square n minus 1, 1 minus alpha. So that means on the right of this the region is 1 minus alpha. So that means on the left of it the region is alpha. So that means c by sigma square is nothing but chi square n minus 1, 1 minus alpha. So UMPI alpha test is phi naught x if c is same as sigma naught square by chi square n minus alpha. So that means 1 if summation xi minus x bar whole square by sigma naught square is less than chi square n minus 1, 1 minus alpha, 0 otherwise. So we could get the UMPI alpha test through the first principle. Now the question is, can I get this directly? Now note that if you apply this test and use the theory of uniformly most powerful unbiased tests for exponential families, it so turns out that phi naught x is UMPU alpha test for testing h naught against h1. So let me write down. So there could have been alternate way. Phi naught is UMPU alpha for h naught for testing. This you might have done in last course, but you can use the result which I introduced in the first few review lectures of testing of hypothesis. You can take this as an exercise. Of course, you must have already done this in the last course. So the only thing, if I can show that my phi naught is uniformly most, phi naught is invariant, then I am done. Now the group of transformation is nothing but x1 plus c, xn plus c. Now note that if I change here x to x1 plus c, x2 plus c, xi goes to xi plus c, x bar goes to x bar plus c, so cc gets cancelled. I get phi naught of x1, x2, xn only. So this is same as phi naught of x1, x2, xn for every c belonging to R. So that means phi is invariant under additive group G. And your G here is characterized by an index C, which is a subset of R. So this implies that phi naught is UMPI alpha. So one could have used the indirect argument also. So this was for this module. Next module, what I can do is I can consider one more example. And then that would be the end of invariant testing. And after that, we can move to sequential probability ratio tests. I'll come to that. I'll elaborate upon that later on. So this is all for today's lecture. See you in the next module, in which I'll conclude the invariant statistical hypothesis testing. Thank you very much.